So I'm going to talk about some thin sets and counting rational points on these. And this is joint work with Tijs Buggenhout and Cluckers in Santens. So before introducing what thin sets are, let me just set up some notation on heights and on counting rational points. So if I take some rational point in projective space, then you can always assume that all coordinates are integers and they are equal prime. And if you do that, then the height of this point is just defined to be the maximum of the absolute values of the coordinates, and this is just some measure for how complicated this rational point is. And now if you have some subset x in Pn of q and some integer b, you can look at this counting function nx of b, which is just going to count the number of rational points on x, or just, well in this case, just the number of points on x, whose height is bounded by b. And this is always a finite set, so this makes sense. And we will be interested in studying the behavior of this kind of function. Also, I mean, in the previous talk, this appears a lot in number theory, trying to understand this function, maybe for specific varieties x, or for other types of algebraic sets. So for us, these will be thin sets, these sets x. And we will be interested in upper bounds on this kind of quantity. Then there's one more. So there will be some interplay between projective, subsets of projective space, and subsets of a fine space. So if I have some subset of A and Q, then there's a corresponding counting function, but this time we count the integral points on X. So that's just all integral points in this box, which also lie on X. Yes, there's a question.
For your specific choice of height, is it a priori like, is n of xb always going to be finite for every x?
Yes, because it's always bounded by the counting for Pn. And for Pn, it's, well, I can write it down, but so let me give two examples for this. So the easiest one is if you look at projective counting on all of An. So what is this? You just have n integers. They must lie between minus b and b. So this is 2b plus 1 to the power n. And the analog for projective space, well, this time we have n plus 1 integers. They must lie between minus b and b. So you expect something of the form b to the n plus 1, but they should.
They're integers. We're not counting rational points? Are we not, we're not counting integer points, not rational points?
But it's the same on projective space, because you can always rescale.
Okay, no, that makes sense.
But there's an extra condition, namely they have to be co-prime. So there's a constant in front, which is a probability that n plus 1 random integers are co-prime. And then there's an error term. Okay, and so the general theme of the talk will be to try to find upper bounds on these quantities when x is a thin set. So I will define what thin sets are. Okay, so there's two types of thin sets of type 1 and 2. And the ones of type 1 are a bit simpler, and much more is known in this case. So I'll first talk about these. So a subset A in Pn of Q, or maybe in a fine space, is called a thin set of type 1. If A is not Zariski dense. In Pn or in An. So equivalently, there exists some closed subset Z, proper closed subset of projective space or of affine space, such that A lies in the set of rational points of this subset Z. So we want to count rational or integral points on this set A, but we might as well look at all rational or integral points on subvarieties of Pn or of An. So let me give you an upper bound for this counting function in this case, which is sort of a trivial bound, and then there's conjectures that you can do much better than this trivial bound. So for the trivial bound, let's first do a affine case so that x in An be some algebraic variety of degree d in pure dimension m. Then this counting function is bounded by d times 2b plus 1 to the power m dimension of x. And the proof is quite simple. Or I will sketch the proof. So you induct on m, where if m is 0, x is a finite set. It consists of at most d points, so certainly there's at most d integral points. And for the general case, let me just make a picture. So here is x. Then what you can do is intersect x with some hyperplanes, let's say where we fix the last coordinate, xn. Let's say xn is equal to c. C runs from minus b to b. You intersect x with each of these hyperplanes, and you get a variety of one dimension lower, but of the same degree, and then you just apply the induction hypothesis to this one. So note there's no assumption of irreducibility or anything in this statement.
What does pure dimension mean?
It means that locally it's always of dimension m. So it's not like a curve and then a bunch of points. Otherwise also degree maybe doesn't make sense. Okay, so this is sort of a trivial bound. Let me also mention we can deduce from this one corresponding bounds for projective varieties.
In this proof, what if one of the slices is
yeah, good question. I was hoping no one would know. Yeah, it can happen that if you intersect x with this hyperplane, that you get something of the same dimension. Right. So what you can do is first you can assume that x is irreducible because this bound is additive in the components of x, and then there will always exist some choice of coordinate for which this doesn't happen. Yeah. So this is the more precise version. So for a projective version, in setup you have some pure dimensional projective variety of degree d. Then this nxb is bounded by d times 2b plus 1 to the power m plus 1. So it's slightly bigger than here. And to prove this, you can look at, well, x is a variety in Pn, but you can also look at x as a variety in an plus 1, just by considering the same equations. And this is a variety of the same degree in 1 dimension higher, and it's an affine variety. Now you can just count integral points on there and use this bound that we have. Okay, so this is some kind of trivial bound, and it's optimal, for example, if x is a linear space defined over Q, then you should expect roughly this many integral points on it. But you should expect much better if x is irreducible, and this is precisely what Serre conjecture says. And a different version of this conjecture is due to Heath-Brown, which I will also mention. That's x in Pn be an irreducible variety of degree at least 2 of dimension n. Then this counting function is bounded above by b to the m plus epsilon. And this notation here means there's some, for every positive epsilon, there exists some constant which depends on x and epsilon such that this holds up to this constant. Okay, so you see this is, it improves this trivial bound by a factor b. And you can also see that this is the best you can hope for. For example, x might contain a codimension 1 linear space defined over Q, and in that case you really should have at least b to the m rational points of bounded height. Nice. Okay, and the Heath-Brown version is very similar, but it's a uniform version. So the only difference is that now this constant doesn't really depend on x anymore, but only on the degree and the ambient dimension. And this is often more useful in practice. Maybe you have some family of varieties, you want to apply it to each member, then you know this constant is independent. And maybe also if you want to do some induction arguments, this kind of family thing pops up naturally. Okay. So there's been a lot of work towards this conjecture. So already Serre observed that you can prove it with an exponent of the form m plus 1/2. So this wins 1/2 over the trivial bound. But the first instances of this conjecture are due to Heath-Brown. Who proved this for curves and for surfaces based on a periodic adaptation of the determinant method due to Bombier and Pila before that. And then there's work of Browning, Heath-Brown, and Zaldanger. When the degree is at least 6, and I will talk later about how we prove this. And this is also, both of these theorems are also the uniform version, so it's a bit better. And then finally, Zaldanger proved this full version of this conjecture. And so it's this version of the conjecture. So it's even this uniform version except when the degree is 3. And that's still open. So for degree 3, we don't know this uniform version. This will be some years.
How do big degrees make it easier?
Because maybe, that's a bit tricky to explain. Maybe.
Then I'll explain it.
Maybe often you expect even fewer points. Maybe.
Yeah, that's a good
when
point.
the degree is large.
Yeah, like
It's
if you're
harder, it's harder for the equation to be whole because when you plug in the numbers into the higher degree polynomial, it's less likely to get zero because it's bigger.
And the reason that d equals 2 is easier than d equals 3
is because it's
because
quadratic
quadratic
forms.
forms.
Yeah, exactly. Yeah, these 2 is also due to in any dimension. And this is from around 2009, maybe 2000. Okay. And I should also say, in recent years, people have been looking a lot at what this constant actually is. So nowadays, it's known that there's no epsilon due to Walsh and later Castric Manuel. And nowadays, we know that the constant is of the form d squared times some logarithmic factors. So Raf also talked about this during his talk. Okay, any questions?
The conjecture is really over non-fields and proven over non-fields, or is it?
Yeah, it's known over global fields. Also should mention this, everything I say will also works over global fields, but I will stick to Q, so it's easier. Okay, so these were thin sets of type 1, and there's also thin sets of type 2. And the definition is a little bit more complicated, so let V be some irreducible variety of dimension n, and phi is a dominant finite map of degree at least 2. Then the image of the rational points is called a thin set of type 2. Okay, so this map is dominant, so I mean, general point of Pn is in the image of V, but you should expect that the image of the rational points is much smaller inside of here. One small remark. So this assumption on degree means that just that this function field extension is of degree E, so it's strictly bigger than 1. Okay, let me give you I should also say, you can also do it with AN, and then you get a thin set of type 2 in AN. So let me give you an example of a thin set in AN, which will be related to solvability of certain polynomials over the integers or over Q. So let's take some polynomial f. In variables x1 up to xn and y, irreducible, and let's say monic of degree E. So it's of the following form. then we can look at the vanishing locus of f in an plus 1. This will be v, and the map phi will go to an, and it's just projection onto x. And then the image of these rational points on V, this is a type 2 thin set. But so what is this set? This is a set of x's in an Q, such that if you plug in x in this polynomial, it has a rational solution. So basically we're asking about solvability of some polynomials over the rationals. And we want to count integral or rational points of bounded height on these sets. If you want an even more concrete example, if you take in the previous example y squared minus x, you will get a set of squares in A1, of course. And usually, I mean, these, there's much less squares than non-squares, of course.
Does this also work if you take f to have more y's, like y1 up to yk, or does it then break?
But then the dimension of v will be too large. Yeah, so later I'll give a lemma that shows that actually every thin set of type 2 comes from some solvability of certain polynomials over Z.
You don't want subsets of that's to be thin.
Yeah, I guess there's various definitions, yeah. I mean, since we're only interested here in counting rational points, it doesn't matter if we can do things. Okay, so what's the trivial bound for counting in this case? So x, let's say, in Pn Q is a type 2 thin set. And clearly NXD is bounded by just counting all rational points on Pn, which is bounded by v to the n plus 1. And similarly, if x in a time space is a type 2 thin set, then the integral points on x are bounded by those on a time space, which is bounded by v to the n. And so Serre's conjecture is about improving this trivial upper bound again. But only for projective varieties, or type 2 thin sets in projective space. Conjecture is following that x in P and Q be a type 2 thin set. Then the number of rational points of height at most b is bounded by b to the power n. And again, there's some constant which depends on x and some epsilon, maybe that's needed. But so this improves upon this trivial bound by 1. And say I already observed that you can prove it with n plus 1/2. only general result is due to Vermeulen, who proved this for dimension at most 2, so for curves and surfaces. And then there's some results in special situations where X is maybe of a special form in recent years. So what we do is we prove this conjecture. At least when this morphism has degree at least 4. So at phi from V to Pn, the finite dominant of degree at least 2. Then the number of rational points height at most B on the corresponding thin set is bounded by B to the n. The degree is at least 5. There's some logarithmic factor if the degree is at least 4. And then we also have some improvement upon the trivial bound for degrees 2 and 3, but it's not quite Serre's conjecture. So it says b to the n minus 1 plus 2 over square root e. When this morphism has degree 2 or 3. Okay. Any questions so far? Yes.
Do you need to make some sort of restriction on the particular type 2 thin set for Serre's conjecture? Because the map where you just send maybe one coordinate to its square, I feel like best you could say was a square root on that.
Yeah, so that's a good point. So in this example, you will get something like or it will be b to the 1/2, but this is an affine situation.
Mm-hmm.
So this conjecture is really about type 2 thin sets in projective space.
Yeah.
And for affine, in affine space, this is not true. As this example illustrates.
But these kind of examples, you can't cook them up into projective.
No, not really. So if you try to do this square thing, for example in B1, then it will still be bounded by B.
Yeah, because you left the. Thanks.
Before B, C, F, D.
Ah.
I can guess one of them.
Yeah. So should I not write?
You wrote them at the very beginning, I think.
Yeah, that's
Oh,
true.
it's the same people as before. Okay.
So, do you, maybe I'll talk about this, but can you make constants depend on like degree of V and E and all this stuff?
Yeah, that's not so clear, I think. Like, I mean, this is just some map phi. It's not so clear what the degree of V maybe means, or yeah, it's not so clear what data really goes in to make this constant. But we do have some more uniform versions, but not for statements of this type. But then, yeah, we'll get to that later. We first transform this into some solvability of polynomials, and then we understand better what this constant is. Okay, so now I want to talk about proving this kind of statements, both for type 1 and type 2 thin sets. So first I want to focus on thin sets of type 1. Okay, so we have some subvariety x in Pn. irreducible. And this conjecture of Serre asserts that this is bounded by b to the power dimension of x. This counting function is bounded by b to the power dimension of x plus epsilon. So a first general reduction is that you can assume that x is a hypersurface. And this is just by some general projection argument. You project x until to like b to the dimension of x plus 1, and generically it will be a hypersurface. And well, you should be a bit careful with this projection that you can still relate to counting of rational points on both sides. Okay. Now, the observation of Browning, Lee, Brown, and Selberger to prove this conjecture is that there is an analogous affine situation here, which is easier to prove and which implies this projective situation. So why are affine situations better or easier to prove? They're more suited to induction arguments. So if I draw this image again, with the variety x, if you want to do induction on dimension of x, one way to do it is to cut with hyperplanes and try to do the induction hypothesis on each of these hyperplanes. So in a fine space, if you want to catch all integral points of height at most b, you will need roughly b hyperplanes. You just take x n equal to c for c going from minus b to b. So that's good enough for this kind of bound, because if the dimension of x increases by 1, you get an extra factor b here. But if you try to do this in projective space, it doesn't really work, because if you want to catch all rational points of height at most b in hyperplanes in projective space, you will really need more than b hyperplanes. So the first insight is that there is an affine situation which is better suited to induction. So what's this affine situation? Well, we already saw this trick. If you want to bound nxb for some projective variety x, you can look at the affine cone. And we want this to be bounded by b to the dimension of x, roughly. So if you want a corresponding affine situation, it should be the following: that if you have y in an, some irreducible hypersurface, degree at least 2, and you count integral points on y of height at most b, then this should be at most b to the power dimension of y plus epsilon. And maybe I should add the assumption that y has dimension at least 2, because once you take an affine cone, you'll always get something. I mean, the dimension increases by 1. Now, the problem is that this statement is false, so it would be hard to prove. And for example, you consider the variety x is y to the d in a affine tree space. So if you count integral points on here, well, there's a third variable z, which you don't see. But z runs freely from minus b to b, so that's roughly b. And now if you fix y between minus of absolute value at most b to the 1 over d, you get some x of absolute value at most b. So this counting will be of order b to the 1 plus 1 over d, which is bigger than what this says. So the solution is to add some extra assumption to y, so that you can hope to prove this, and which is always true if you take an affine cone of a projective variety. So condition is the following. So y is defined by some polynomial f. Of degree d. And I'll denote by fd the degree d part of f. So what is this? For example, if f is maybe x cubed plus xyz plus z plus 1, this is of degree 3. Then f3 is just you collect all degree 3 terms here. Okay, and then what Brown and Salberry prove is that if d is at least 6 and fd is absolutely irreducible, then this bound holds. Now we can actually do better than this. So maybe first of all, where does this condition or where is it used, this absolute irreducibility? It's used to bound the contribution coming from codimension 1 linear spaces on y. So you expect that if you have some variety y, that the rational points or the integral points will sort of be dominated by counting on codimension 1 linear spaces. And this assumption is needed to control this contribution. Yeah, but there's a second, you can improve this result. Namely, the real reason this example goes wrong is that it's actually a curve, because there's only two variables. There's some variable z, which you don't see. So if you exclude all varieties which are secretly curves, then you can still prove this kind of bound. So assume that for every q linear map or q linear projection, phi from an to a2, phi of y is not a curve. So this example, there's clearly a projection to x and y, so it's a curve. Then this bound also holds. And this assumption, absolute irreducibility of fd, implies this one. So this is much weaker. Okay, so this is how you prove these kind of things. Well, then still, you have to prove the induction basis, which is surfaces, which is not easy, but I will skip this.
Your improvement works for degree at least 6?
No, it should be at least 4. But also this, Salberry improved this to d at least 4.
For the surfaces, can you use Broberg's results, or do you need to reprove things?
Sorry?
For the surfaces, case, can you use Broberg's result, or do you need to reprove it?
For which, for affine?
You're saying in the base case is surfaces.
Yeah, that's for affine.
So you can't use.
Yeah, Broberg is for.
Broberg is for type 2.
Yeah, that's true. So he proved it for projective surfaces. And he does actually do induction on dimension, where he uses the proof for curves, but he chooses some good collection of hyperplanes to do induction from surfaces to curves. Okay, so for type 2 thin sets, the first step is to use, well, the strategy is roughly the same, so we find some affine analog of this and then try to prove this by induction on dimension. So the first step is to go from this situation of a map from some irreducible variety to Pn to some kind of solvability of polynomials over the integers. So let's suppose we have this finite degree dominant map. So then, what does the lemma say? Then there is some proper closed subvariety W, some integer D, an irreducible polynomial f in variables x0 to xn, which is of the following form. So it's monic in Y. And it's weighted homogeneous, so each fi is homogeneous of degree I times d. So if you give y weight d and all other variables weight 1, this is really just a weighted homogeneous polynomial. So conclusion, if you count rational points on this type 2 thin set, then this is bounded by counting rational points on the image of W. So I really mean the image, not the image of the rational points, plus the number of coordinates x, for which this polynomial has an integer solution. Okay, so I don't want to discuss the proof of this, but basically what you do is you look at the extensional function fields, and this polynomial f will be a minimal polynomial of some generating element. And then you will have to throw out at some point some closed subvariety W.
What was the conclusion? That the number?
That if you count rational points on the corresponding thin set of type 2, this is a plus. Then you have to count on the image of this set W.
Plus this, okay.
Yeah, plus you look at all x's for which this f has a solution.
So this means that at the expense of removing a certain type 1 thin set, you can treat it as a hypersurface.
Yeah, basically. Yeah, so this
it's essentially a birational thing.
Yeah, exactly. So this first thing is certainly okay. So what do we want to prove? We want to bound this by b to the n. And this first part is certainly bounded by b to the n, because this image is a proper subvariety of p to the pn. So this just follows from these trivial bounds. Okay, now this situation, so what we have to do is to control this part, and this is not quite an affine situation, because this this f is weighted homogeneous. So what we do is we just look at polynomials like this, but what happens if you dehomogenize by putting x0 equal to 1? And the affine situation is the following: we have some polynomial f in variables x1 up to xn and some variable y, monic in y of degree e. And the degree of fi is bounded by I times d for some integer d. See, and then we look at this counting function, the number of x's in the box. That should be n plus 1 in this. For which there exists an integral solution. This is more suited to induction because you can intersect with the hyperplane in the x variables and get a polynomial of the same shape. But again, the issue is maybe some notation, so I will denote this n of cover of fb, and we want this to be bounded by something of the form b to the n minus 1, maybe plus epsilon or so. Now again, the problem is that this statement is false, because it's some affine situation. You will need some extra assumption. An example is take y squared minus x1 minus x2. And what is this counting? This is counting the number of integers x1, x2 between minus b and b whose sum is a square. And this is at least bounded by b to the 1 plus 1 half. So it doesn't, this bound doesn't hold for this example, so there's an extra assumption that we need to add. So what's the extra assumption? I'll denote by f top, the top degree part of f. So in the weighted homogeneous sense, so more precisely, this is y to the e plus, well, f1 is a polynomial of degree at most d, so we take its degree d part, and f2 is a polynomial of degree at most 2d, so we take the degree 2d homogeneous part, and so on. And then we have the same kind of assumption as in Browning, Hebron, Solvay, namely if this is absolutely irreducible, and so D is at least 4. Sorry, yeah. Then this bound does indeed hold. Namely, so the form b to the n minus 1 times some power of log b. And there's an implicit constant here, which is now more uniform than before, namely it depends only on n, d, e, and the norm of f. So this means the maximum of the absolute values of all coefficients of f. Okay, so why do we use this assumption? So again, there's this, I mean, previously this was used to control contribution from codimension 1 linear spaces. So here there's also some kind of codimension 1 subspaces, which are sort of the analog of the linear spaces, which you expect to contribute the most to counting rational points or integral points. And this assumption is needed to control that contribution. So. Yeah, maybe we should write down one more term. So this is not quite what we actually prove by induction. So what we really look at is the following counting, and we just count the number of x1 to xn and y in z to the n, such that each xi is bounded by b, y is bounded by b to the d, and f of xy is 0. So then we prove that this is bounded by this kind of quantity, and now there is no more dependence on the norm of f. And going from this type of statement to this one is fairly simple. You just have to replace b to the d times by some constant c times b to the d, and this constant will just depend on the norm of f. Okay, I remember I wanted to say something more about this. But so this is the precise statement that we prove by induction on n. So now if you intersect with some hyperplane in the xn's, you can try to apply this induction hypothesis because there's no dependence on anything.